My name is Peter Ashwood-Smith with Huawei Technologies, and my colleague here, Srikanth Kisra from Avaya. And I'm going to spend about 45 minutes or so going through a little bit of an overview / tutorial of 802.1AQ. And then I have a demonstration, and if the connectivity to the labs works, I'm going to log into one of my lab switches and show you a few things. And also Srikanth has access to his lab. I see it's up and running, and he's going to show some OANM and also a small network. So we have some sort of concrete stuff to show. Unfortunately, the fluffy markety type slides are easy to see in the back, but the actual details, which probably people mostly care about, are much more easy to see if you're sitting down in the front. So what's this all about? Essentially, 802.1AQ is aiming to bridge a gap, essentially, between the current spanning tree protocols at the low end and the higher end VPLS type protocols for control of larger layer 2 networks. And so the IEEE is working on a mechanism to address some of the existing issues and move Ethernet forward. So what I'm going to do is I'm going to go through what some of those challenges are, what AQ, shortest path bridging, is. I've got a few slides on applications which I'm going to breeze through fairly quickly because some of them are probably fairly obvious to people. Talk about how it works. I have quite a bit of detail on TLVs and this sort of stuff, which we can either go into in detail or breeze through depending on people's level of interest. And then, as I said, depending on connectivity, I'll log into my lab and show you a 36-node SPB network, and I believe Srikanth has an 8 or 9-node network, which he's going to show you. So what are the sort of the challenges that we're trying to address here? We're trying to make layer 2 networks much larger. We'd like to get into scales of around 1,000 or so bridges, or certainly an order of magnitude larger than we're currently able to do. I want to be able to use all of the mesh. If you bother to put a link in, we want to be able to use it. And we'd like to be able to use all of the shortest paths, or a substantial number of the shortest paths that are present in that topology. I want to be able to do efficient broadcast and multicast, and I want to be able to make use of all the replication points that are possible within the network for the purpose of multicast. I'd like to be able to avoid address learning by any of the tandem switches. I just want to do address learning at the edges to allow the core of this network to scale. And I'd like to get my recovery times into the hundreds of millisecond range. I'd like to do this all without looping, and I'd like to be able to do it not only physically but logically with many hundreds or thousands or tens of thousands of layer 2 VPNs or subnets, essentially. And while I'm doing this, I want to be able to maintain all the existing properties that we have with layer 2 today. I want to be able to have the ordering maintained, the transparency, the symmetry and congruence of the routing, so the symmetry of the unicast and the congruence with respect to multicast. And I want to do this while producing shortest paths. And probably one of the most important bullets here is we have enormous amount of time and energy invested in Ethernet OANM. We want to be able to reuse all of the existing Ethernet OANM mechanisms that are out there today. This is just a classic little example. I'm going to use this network actually throughout my little talk here. This is a 36-node network. I'm just showing a spanning tree traversing this network. The root is over here at node 1, and these sort of pink-colored links represent the spanning tree computed tree. And one of the first things that you see, of course, is I can't use every link in this network. And if I wish to route between two of the leaves of the tree, I have to go all the way up and all the way back down the tree. So it's pretty miserable routing once you get into fairly large scales, or if you're far away from the root. Other problem, of course, is address learning. These addresses out here at the source have to be learned at all the hops up and down the tree if I wish to move packets between the destination back to the source. So these are some of the issues that this work is aiming to address. So what is this protocol? Essentially, it's an IEEE protocol, 802.1AQ, building on top of the existing 802.1 standards. It's essentially a new control plane, but The data planes are not new. Okay, it's a new control plane for both Q and Q and MAC and MAC, so the Ethernet and Ethernet protocol. Some very nice properties of this is that we can leverage all the existing hardware that's out there that supports MAC and Q today. These two modes are referred to as V mode and M mode. It's totally backward compatible to all the AG and the 1731 and the ongoing data center bridging suite of protocols. Provides multiple loop-free shortest paths and allows use of pretty much all of the mesh connectivity that you put in place in the network. Supports currently 16 equal cost multipaths. Because we recognize the fact that this is an area of great interest for people, the protocol supports opaque mechanisms to allow many more than 16 and many more types of algorithms going forward, including hash-based per hop forwarding going forward. Multicast mechanisms include both a typical Ethernet tandem or transit replication model, but also a VPLS-style head-end replication model, and I'll talk briefly about that. One of the nice things about the way the shortest path routing works is that the traffic is assigned to the path at the head end with these the current set of 16 ECNP models. And since these are highly deterministic routes, you can very easily predict where the traffic's going to go with an offline tool. It's going to do exactly what the offline tool will predict exactly what the network's going to do. As I said, up to maybe even beyond 1,000 odd devices, ISIS has already been out there and deployed on very large scales, so we have no doubt that certainly the ISIS protocol and its extensions can go to 1,000 or so nodes without too much difficulty. This is a huge improvement over STP, of course. We're 2 orders of magnitude already beyond that. Obviously, convergence. We'd like to get the convergence to be fast with a minimum of fuss and fiddling. We're seeing in some of our networks, 100 odd milliseconds and below. And I think in one of the actual deployed networks, and Srikanth can correct me if I'm wrong, but it's 50 or 60 odd nodes, and they're showing a 300 odd millisecond on average actual outage times at layer 2. Again, it's an ISIS-based protocol, and ISIS has a number of features that we've chosen to adopt. One is the multi-topology mechanism, so you can create multiple instances of the topology within the shortest path bridging protocol. For example, you could use one of them for server I/O connectivity and one for just multicast video or whatever. You have different options. You can assign these link weights differently. And that's just a normal ISIS multi-topology behavior. The protocol also uses the ISIS protocol for the advertisement of layer 2 VPN membership. So this is very simple. You just go to the edge of the network, configure what the membership attributes are, and what group you're a member of, and the network just automatically computes the appropriate interconnectivity. As I said, the address learning by this protocol is completely restricted to the edge using the MAC and MAC mode. So the forwarding database is computed and populated. It looks a lot like a router. Some of the differences, though, the unicast and multicast are computed exactly the same time. And there are some special properties with respect to the unicast and multicast that the calculations guarantee. In particular, they guarantee that the unicast is symmetric in both directions, and that the unicast and multicast are following the exact same route. And this has rather profound implications on the OANM suite. In other words, we don't break any of the existing 802.1ag and 1731 test suites with this protocol. It doesn't preclude us doing other types of forwarding in the future, but certainly today that's the current model. Because there are 16 different equal cost paths and there are opaque mechanisms for more, there's also a certain amount of tunability, so you can actually tweak and twiddle how the paths are going to go through these networks if you don't like the way the ECNP has actually laid things down. So visually, if you put some of this stuff together, it's probably easiest to understand 802.1aq visually in any routing protocol. Pictures are helpful. But here are all the shortest paths between pairs of sources and destinations, and you can see the corridor between the different nodes. is being well utilized. I've just overlaid all of the different shortest paths simultaneously. So in terms of multicast, what happens is the shortest path trees, which are available from any given node, are used as a template for the multicast. So here's the shortest path tree from node 1 to all of the other nodes in this network. And if I assign a set of edges to be members of a particular group, a particular layer 2 VPN, then what happens is a shortest path tree, a subset of the shortest path tree, is used as a template for the multicast. And so here what's happened is that node 1 has this template of its shortest path tree, or a subset of its shortest path tree, being used to reach all of the other members, and only these members of this service or layer 2 VPN, whichever terminology you prefer. And so what this translates to in terms of learning, the actual data flow, an unknown unicast or a multicast packet originating from node A connected to some LAN hanging off node 1, destined to B off node 20, results in a multicast packet within the SPB network, being multicast only on this tree, only to the other members. It then is learned, the association between node A over here and node 1 in the SPB network is learned at the edge, and then arrives at B. B responds, and since we now know here that A is via 1, A can node 30 here can respond with a unicast packet back to A, and then the learning is complete at the far end here. And these two edges have now learned the association, the inner to outer association, and we're good to go. The actual encapsulation, like I said, in SPVM mode is MAC in MAC, so what you have is the inner MACs here, so either C or SVLAN, payload, source, and dest, and then the 802.1AH MAC encapsulation, which has the destination and source MAC addresses of nodes within the SPB network, and then an indication of the service that this is a member of. So just briefly, some of the applications here before I get into more of the details. 802.1AQ is a particularly good replacement for a protocol like MSTP or STP. If your STP is reaching, or your MSTP is reaching some scales that are starting to scare you, you're running into problems with tuning and tweaking and twiddling, then running shortest path bridging in this context is probably a good option. Unlike MSTP, where you have to create multiple trees to kind of get the balance that you want and the route quality that you want, that's all going to come for free in this context. Data center is another big application that everybody's, a lot of people are busy talking about. One of the trends today in data center networking is to try to create what we refer to as a big layer 2 switch, as a fabric to interconnect the components in the data center. So we might take hundreds of terabit switches and put them in together into a non-blocking topology, or a topology that has sufficient bandwidth from any incoming port to any outcoming port. And why do we want to do that? Well, it allows us to place the servers pretty much anywhere we want around the outside of this fabric. I can place the routers anywhere I want. I can place appliances anywhere I want around this, as if it was just one big switch. And probably one of the most interesting applications is the ability to put virtual machines within the servers anywhere I want on any server hanging off this fabric, and have its IP address be completely mobile, so I don't have to reassign the IP address. If I move the virtual machine around, I can use layer 2 mechanisms to do that. So in essence, what I get is the ability to have any subnet hanging off any port I want anywhere within this fabric, and that fabric might span one data center, or half of a data center, or even several data centers. The fact that we use a non-blocking fabric here, so doubling the capacity as we go up means that my congestion issues are minimized within the layer 2. And being able to use move the virtual machines around is a power savings and just a general energy saving and balancing issue. It allows us to control the cost of operating that data center. The shortest path routing in 802.1aq is something that's particularly important in the context of a data center. So if you look at some of the statistics, certainly some of the statistics we've been getting, something like 75% of the traffic in a data center is actually between servers, not coming into the data center or out of the data center, but actually crossing between the servers. And if you don't have shortest path routing between the servers, then you're going to be doing a poor job of moving traffic between the servers within the data center. The determinism of routing is a very nice thing. Like I said, it allows you to predict what your network's going to do offline. The flexible subnet, the ability to expand and shrink anywhere, is a major attribute of the virtualization and some of the different vendors' virtualization mechanisms. AQ compatible, like I said, with .1 and the data center bridging and O&M protocols. So all of those protocols, the Y.dot and the .1AG, are available across this large fabric within a data center. And of course, address isolation. The virtual machine MAC addresses being isolated is imperative for these very, very large data centers. And who wouldn't want fast recovery and non-looping? This is just one of my colleagues got a little bit carried away with PowerPoint, tries to show the virtual machine motion. And so you have a couple of subnets here. You've got a pink one and this yellow one. And the idea is that I can extend the subnet anywhere I want within the data center and then move the virtual machine. So he's just shown several different examples of virtual machines being moved around and the logical subnet connectivity being extended or compressed to do that. I'll just go through this quickly. Okay. As I said, these VMware mechanisms for moving virtual machines around are very popular in the data center. And so anything operating in the data center has to be completely compatible with these. Anything that sits on top of these VMware type mechanisms is just going to work in an 802.1aq type environment. This also applies to things like the Microsoft load balancing mechanisms. Some of the modes depend on the layer 2 behaviors, and so that's very important as well to be able to support that. Virtual router redundancy protocol and some of its proprietary variations, of course, will just work in this context. So in the data center context, 802.1aq is just making the data center layer 2 portion larger and better utilized, and providing the AH and the AG and the 1731 management mechanisms. This is an example of a kind of a data center fabric that I'm talking about, and I'm not going to go through this in gory detail, but essentially what you've got here is almost 100 or so terabit switch fabric, where you have 16 spine nodes with 100 gig E-links going down to 32 aggregation, or whatever term you want to use, devices on the bottom, which are talking to 5,000 servers with 2 times 10 gig E each. So that's a pretty substantial layer 2 fabric, which a protocol like 802.1aq can support. That's like it's only 48 nodes, which is trivial for a protocol like ISIS. So this is the kind of application either in a data center or a high performance computing environment that we expect to see going forward. The Metro, where the layer 2 VPN is a major component of building up a metro, where you either provide ELAN, E-line, or E-tree type services. So you can think of 802.1aq in this context as a very cheap form of VPLS. It can do VPLS style head-end replication, where it interconnects, does serial unicast. to replicate packets, or it's able to do the point-to-multipoint style transit replication just through calculation. So it's a very, very lightweight way to do what VPLS plus point-to-multipoint, RSVPT, and so forth are doing with slightly different trade-offs. An E-line is just a two-member ISID. An ELAN is a service that has more than two members, both of which are transmit and receive, and a tree just has one transmitter and multiple receivers. So by playing around with an attribute of membership and an attribute of transmit and receive, we can create a wide variety of different types of connectivity model. And we'll skip over that for time. All right, so let's go into a little bit of the detail of how all of this works. From the person operating the network's perspective, it's all pretty straightforward. You plug the network to network interfaces together, and ISIS just brings up the network. There's nothing much to do there. You then group the ports either by CVLAN, SVLAN, so either logical or physical ports that you wish bridged, and you have up to 2 to the 24 of such groupings because of the MAC and MAC encapsulation. And you then assign an ISID or a service identifier to each one of those. Right? It comes up, and you then have the AG OANM suite available to manage things and with all of those great features. Internally, though, within the box, what goes on is that ISIS will read the pre-assigned MAC address which comes with this box and form the network-to-network adjacencies and advertise those box MACs. So you don't have to configure any addressing here. ISIS will then read the uniport services, so the ISID information that you've configured on the edge of this network, or which could actually be learned, but protocol doesn't really care how you get it. Advertises that service information together with the topology information, puts it into a calculation machine, which then produces the forwarding tables that bridge all of those service members together with those properties that I just described. So the MAC in MAC data path at the ingress, what it will do is it will take the tagged or untagged traffic arriving at the uniport. It will encapsulate it with the box MAC, the SA of that ingress device. It will encapsulate it with the service identifier, which is associated with this group, so what VPN you're a member of. It will then encapsulate it with a VID, which has been either pre-assigned or chosen based on the route that you want to use across the network, and then it will do the actual lookup of the end host DA. If it finds that end host DA, then it knows what the appropriate egress shortest path bridging device is, and it will then just assign it and send it unicast. The more interesting case is if it hasn't found it, and of course now you have to do a multicast to find it, and there are kind of two modes there. One mode is if you are using a transit replication or you're just doing head-end replication. If you're doing head-end replication, there's not much to do except just send a serial unicast, a copy to the other egress points. More interesting if you're doing multicast, true multicast, in which case you have to actually produce a multicast header which indicates where the packet has come from and which group it's going to. And I'll show you what that looks like in the next slide. The unicast transit is pretty straightforward. There's a unicast shortest path from a node to all the other nodes, and that's just computed using standard Dijkstra type mechanisms. And the BMAC or the MAC address, the box MAC of each of those devices, other devices is installed in the forwarding database with the outgoing next hop appropriate for the shortest path to that device. And you can think of it as being repeated 16 different times. It's actually not, but logically you can think of the algorithmically as there being 16 computed shortest paths with different BVIDs for each one. So if you had a 1,000 node network, that means you use 16 BVIDs in the entire network for this routing. The symmetry of routing is one of the more interesting aspects of this protocol, and the symmetry is assured through special tie-breaking logic. When you have two competing shortest paths, you need a deterministic tie-breaking mechanism so that every node in the network will produce the same result, and this is done through the logic of the tie-breaking. I'll go through that in a minute or two. So visually, this is what the, an example of the unicast forwarding table would look like. So here we have 4 shortest paths, 4 equal cost shortest paths, purple, the yellow, the blue, and the red. And the node on the left, 1, has four entries in its forwarding table, each one distinguished by BVID. So we can see if I want to get to node 4 using the first route, then it's interface 9, etc. And the symmetric routing on the other side, well, you can see for yourself, right, that the upper path is via the outgoing interface 3, which is the same as its incoming interface. And so this would be consistently done throughout the entire network. The multicast transit is actually quite interesting, except in the case where we're not asking for tandem replication, because if I'm not asking for tandem replication, in other words, the replication is being done at the head end, then there is no multicast state in the core of the network. So there's nothing to talk about. It's just like VPLS. It's boring. What's much more interesting is if you select the option that says, well, I'd like the multicast to be done by the transit nodes, then the transit nodes have to create multicast state for that. And the way they do that is by asking themselves, and I always describe this in English, I'm a node, am I on a shortest path between a node A, which is a transmitter for some group, and a node B, which is a receiver for that group? And if I am, then I will install forwarding state. I will actually merge forwarding state into the set of forwarding state for that multicast group to the interface towards B. So in other words, it's really just a question of replicating all the forking points in the shortest path tree. If I know what the shortest path tree looks like, the fork point in the shortest path tree is exactly the replication point for the nodes that are on that tree downstream of the transmitter. Now, in order to make this work, I need a multicast address format, a new one. And so what we have is we have a locally manufactured multicast address within the core of the SPB network. So the first thing is that the local bit and the group address bit, of course, are set. The low order 24 bits are telling us what group this packet is a member of, and then the remaining 20 bits are saying where did we come from. So there's a 20-bit unique identifier of the node within the network. So if you combine those two things together, I can tell you where the packets come from and exactly what group it's a member of. And this doesn't change as the packet flows through the network. So what does this look like visually? Here's that same little 6-node network, and I'm showing the shortest path tree, the subset of the shortest path tree that reaches nodes 1, 3, and 4. So I have this little group 255, which has the membership 1, 3, and 4. So node 1, if it wishes to originate packets which are going to go to the other 2 members of this group, launches a multicast packet with a header that says, the destination address says I've come from node 1 and I'm a member of group 255 using the format that I just showed, and it'll pick the BVID according to which route that it wants to use, which shortest path tree it wishes to use, and of course the outgoing interface from node 1 is 10, and node 6, because it's doing replication, has 2 outgoing interfaces for the same multicast address, the same BVID, 5 and 6. So if you put all of that together, what you end up with, and what I'm showing here, is a set of 8 nodes which are members of a particular ELAN or ISID or service, whichever terminology you want to use, 255. And so what I'm showing here is a superposition of all of the subsets of the shortest path trees from each node to all of the others. So we actually refer to this as an active topology. This is the subset of the full network which will be used for the purposes of traffic between these nodes on this ISID. And that's the shortest path tree from node 1 to the other members. And that's the shortest path tree from node, I think it's 30. I can't see behind the green, but I believe it's 30. That's the shortest path tree from 30 to all of the others. And this immediately highlights the important property of these particular ECMP algorithms, that they are symmetric. So that sort of circled or oval circled set of hops that I've shown you are not only the unicast path, they're the multicast path for packets going between the green and the blue. And that property is true everywhere within this active topology, and that is the property that enables us to do a couple of things, one of which is maintain the 30 years of OANM, or how many years of OANM work we have in Ethernet. Maybe not 30, but as I said, the fork points in these trees become the replication points for multicast if I'm choosing to do transit replication. Otherwise, there is no multicast state, but these are still the unicast routes that are used in the case where replication is being done at the head end. The actual control plane protocol, like I said, it's ISIS. It doesn't require us to use IP to operate. That's why we picked ISIS. However, it doesn't preclude the use in parallel of IPv4 or v6 or anything else that ISIS is capable of carrying. The sysid essentially carries the VMAX, the box MAC address if you're running it standalone. There are no new PDUs or any real substantive changes to ISIS except the addition of 8 new TLVs. Very quickly, some of the TLV data that's added, we add information about, in the hello protocol, we add information about what ECMP behaviors, what equal cost behaviors we're using. We have a new network layer protocol identifier specifically for AQ, and the link costs, we have a parallel set of link costs which are advertised specifically for SPB, which allows us to have different link costs. If you are running V4 or V6 or something else in parallel, they can have different link costs. And again, you can even have several different instances of SPB by virtue of the multi-topology extensions. The service information is also, as I mentioned, also advertised in the link state protocol. So all of the attachment points and what services they're a member of are also advertised in the ISIS protocol. So we only need one protocol to do all of this. I'm not going to go through this right now. In terms of tie breaking, as I said, the tie breaking is sort of one of the things that makes this first set of ECMP behaviors that AQ supports rather interesting and allows us to operate with the existing OANM suite. In order to keep the forward and reverse and the unicast and multicast congruent, we need a symmetric distributed tie-breaking mechanism. So every node in the network has to uniquely, deterministically produce exactly one shortest path for a given desired ECMP behavior. And one of the rules here is that the shortest path from A to C has to be made up of shortest paths as subsets. In other words, it has to be transitive. The shortest path from A to C must be made up of a shortest path from A to some intermediary B, and then from B on to C. And that's pretty important, because if we don't do that, we can't actually do hop-by-hop forwarding based on a destination. I actually have to look at the source and the destination to do the forwarding if I don't support that. Now, in order to compute these symmetric shortest paths, what we do is we have a unique identifier network-wide that tells us, that identifies a path. So that unique identifier, we refer to it as a path identifier. And this is actually not how the algorithm works internally. This is a way of thinking about it. And a path identifier is essentially just a sorted list of the nodes between the source and the destination, not including actually the source and the destination. So if I have a choice of several equal cost paths, the distributed tie-breaking rule is, for one of the algorithms, to pick the path that has the smallest path identifier. And so here's what that looks like. If I have these 4 different paths, the path identifiers for the purple path is 2, 3. The path identifier for this red path on the bottom is 5, 6 because it's sorted, and likewise 2, 5 here for this orangey yellow one, and the blue one is, of course, 3, 6. And if I look at these things now, rank them, 2, 3 is the smallest of these, and so every node in the network can produce that, can do that calculation and say, okay, this particular path is the one I'm supposed to have picked for this particular ECMP behavior. Now, what we do in order to produce all of the other different paths is we simply apply bit masks to the bridge identifiers. So I can, if I invert all of these bridge identifiers and then run the same algorithm, the smallest under inversion is actually the largest path identifier. And so I end up with this red path. And so that's actually the second ECMP behavior. And then there are 16 essentially bit masks, each of which is successively used to produce a different ECMP behavior. So each one of those bit masks will produce a different SPF or a substantially different SPF tree under ECMP with respect to the others. Now, we also have the ability to tune these. So some of the bits within this bridge identifier are actually referred to as a bridge priority. And that bridge priority, because it's appended to the bridge ID as part of the ECMP behavior, that bridge priority can be tuned up or down, which gives you a certain amount of flexibility with respect to how these things look when they're tuned. And here's an example of how that behavior works in something fairly real. This is that 16 by 32 fabric that I was talking about. So 16 spine nodes and then 32 aggregation nodes connected off there. And so you can actually have all 16 of the uplinks available, usable. And what's really quite interesting is that in the case of multicast, each one of those 16 spine nodes will actually be picked successively as a replication point by each of the different ECMP algorithms. So not only do you have a good balance with respect to unicast, but you have a pretty good balance available to you with respect to multicast as well. In terms of loop suppression and avoidance, there are kind of two mechanisms here. The AQ protocol supports a suppression mechanism which is based on a reverse path forwarding check. We refer to it as an ingress check, but it's really just a reverse path check. And what you do is you look at the SA. So this little algorithm here is pretty much exactly what the forwarding plane does. It takes an incoming packet and decides whether or not to discard it based on whether looking up the packet in the forwarding table produces an outgoing interface, looking up the SA, in the packet that's come in the layer 2 forwarding table, finding what the outgoing interface would have been for that SA if it were a DA, if it were a destination address. And if that's not the interface that the packet's just come in on, then we throw the packet away. And you can sort of see that here, that you reach a point in a loop where there's an ambiguity with respect to the incoming interface and the forwarding table. What's very nice about this mechanism is that it has no impact on convergence rates. It just runs in the data plane. It's based on the actual learning mechanisms. Most of these layer 2, most of these ASICs, most of these ASICs have, well, they pretty much all have a learning mechanism, but many of them have a programmable mechanism for turning the learning either into a discard or an interrupt to the control processor. So by turning the learning mechanism into a discard, we can actually implement this reverse path forwarding check. In terms of loop avoidance, a little bit more sophisticated mechanism, it's a control plane mechanism. And what happens with the control plane mechanism is that the topology, the hello protocol is augmented with digests of the topology. And so when two nodes, when every node in the network or the nodes in the network agree with respect to the topology, then there won't be any loops because the control protocol will have produced a correct loop-free topology or set of forwarding. The possibility of a loop occurs, however, when there's a disagreement. So if we can quickly detect when there's a disagreement with respect to topology, we then have a handle that we can use to decide whether we need to block some of the forwarding entries or not. And you don't want to block all of the forwarding entries, so what you do is you separate the forwarding entries into safe and unsafe subset. The safe subset is allowed to keep forwarding. The unsafe subset has to be blocked. And then it comes down to what is the definition of safe versus unsafe. And the easiest way to try to describe this is that in order to create a loop in a piece of string, I need a certain amount of slack. I need to be able to stretch it a certain amount and fold it on itself. And so mathematically, if I allow a root to move more than a certain distance, if I bound the amount of motion with respect to that entry, I can avoid it folding beyond its neighbor. So in other words, I allow a certain amount of slack in the distance that this thing is allowed to move, and by knowing what the allowed slack is, and if everybody agrees what that slack is, then they can never fold, and I can partition the entries into safe and unsafe based on that. This is a fairly deep topic. There's a whole lot of material on the proofs of correctness of this, and if somebody is really interested in going into it in detail, we can give you some material on it. In terms of OA&M, as I said, the entire 802.1 AG and 1731 protocol suite is available, and Srikanth is actually going to show you in his lab some the layer 2 trace route, ping, and so forth, which already existed and only required moving to the AQB vids in order to implement. This is just the full suite of stuff that is available, obviously, with the AG and 1731 and so forth. I'll just point out, though, that some of these mechanisms depend on symmetry and congruence in order to produce accurate answers. So it's one of the reasons why we chose to adopt these mechanisms for these initial ECMP behaviors. In terms of the management, you can manage 802.1AQ with existing ISIS MIBs plus some additional information which is going to be added to those MIBs. But we've also created a standalone MIB. The standalone MIB allows you to treat SPB as a standalone network, of course. Includes things like the basic configuration data, dynamic information, adjacencies, the list of SPB nodes in the topology with respect to whatever multi-topology we're using, list of edges, and then the services within the network. It's pretty much what you'd expect in terms of the objects and tables that are required. In terms of the TLVs, as I said, there are about 8 of them, and I have in this slide deck a sort of a list of each of them. I'm not going to go through them in gory detail. I will just point out, for example, the extended link metric, a new link metric for the purposes of SPB, and the service information where we advertise the ISID and its transmit and receive properties. And there's an IETF draft which has all of this stuff listed out, and folks are welcome to look at it if they want to see all the bits and bytes. Okay, so what we'll try and do now is we're going to try and go through a couple of short demos. I have in my lab in Ottawa a 36-node network like this, where these are actually 4 real nodes, and the rest of it is an emulated network. And I have configured this service 255 as I've shown here around the edge. And this is physically what I have in my lab. I have 4 of our smaller terabit switch routers with these services coming in on these ports here, and this dual home type connectivity to these two other switches. I have a Linux server which has 6 interfaces going into these 4. And then there's a PC which is used. You can draw the network, and what the PC does is it injects the topology into the Linux server, and the Linux server then creates as many ISIS instances as it needs to represent each one of these logical nodes, with the exception of the physical nodes out here. And the ISIS protocol doesn't know that it's not running within a real switch, so it just forms its adjacencies over these little fake adjacencies within the Linux server, but some of the adjacencies are real to this physical switch. So in summary, it's 36 nodes, 172 links, and in this particular module there are actually 2 services, but I'm only going to show one of them. All right. So first thing I'm going to do, assuming that I haven't lost connectivity to my lab, is I'm going to show you node 3, and I'm just going to show you some of the brief shortest path bridging data, the ISIS peers, and then I'm going to go through, show you what the LSDB looks like and so forth. So I'm going to keep going back and forth from this window to my CLI window, which should be back here, and we'll see if it's still up. Yep, it's still up. Okay, so this is just a simple display shortest path bridging command. I can see the current MAC address for my switch number 3. I can see the short form of name of this device, which is used for the formation of multicast packets leaving it. And I can see that I've actually configured 2 ECMP here for VLANs, BVLANs 100 and 101. And here are my 3 peers, okay, 2, 1, 4, 5, 15, and 17, which correspond to this picture here. So this is what you're seeing. We can take a look at the link state database, node 3. We can look at the ISIS link state database, and what we should see is 36, where we're node 3. So this is the one with a star. So I'll just go over here and do that. There we go. So we can see all 36 nodes in this network. So the next thing we'll do is we'll take a look at the link state database entry on node 3 that originated on node 1. And since node 1 has service membership, what we expect to see is within the detail of this link state database entry, we expect to see information about the service. And indeed, this is what we're going to see. We're going to see the 2 neighbors, 3 and 4. And we're also going to see some ECT information about what node 1 thinks it's doing with respect to ECMP. And then we're going to see the service 255, and that node 1 is a transmit and receive member of that for a particular BVID, so a particular routing that it's asking for. So we'll do that. And this, I always type this command wrong, so I should have it in my buffer here. There it is. So yeah, that's displaying the ISIS link state database for node 1, and we're on node 3. And so here it is. Here are the 16 ECMP behaviors. There's only 2 of them configured. We can see the two neighbors with their costs, and then the 2 services. So the 255 service is the one we're talking about, with both transmit and receive membership. So that's sufficient information for the computations now. And so what I'm going to do next, I'm going to show you, we're going to look at node 3. We'll look at the unicast routing table, which essentially is a list of BMACs. And we're going to look at the unicast routing table for SPB, and we'll look at the route from node 3 to node 16. 16, of course, is 10 in hex. So we're looking at the 2 entries for this SPB device 10 on the BVLAN 100 and 101. The 101 is this northern route, and the 101 is this southern route. So one of them is on interface 16, and the other one here is on interface 18. So I'll just go over here. The unicast MAC table, and we should see that. Where is it here? Work. Right here. Oops, I selected one too many, but you can see it there, the 10 on 16 and 18. So unicast traffic coming into this node heading to 10 with BVID 100 will just go to the GIGI interface 016. Okay. So where it gets more interesting now is the multicast forwarding. So what I'm going to do is I'm going to show you for node 1 traffic originating for this service from node 1, what node 3 does. Now, because node 3 is a fork point in the shortest path tree from node 1 to the other members in this this service, this ISID, there will be multicast state here from node 1 to replicate out of these two interfaces for ISID 255. And likewise, if we have traffic originating, I believe this is node 26, since node 3 is a replication point, a fork point in the shortest path tree from 26, it will have entries to replicate traffic to node 2 and node 1 if it's come from node 26. Now again, I've asked for full transit replication in this network, so I get the multicast state, but I don't have to have the multicast state in this context if I choose to use the head end to do replication. So this particular service, some of the attachment points could be doing head end replication, some of them could be doing transit replication. In this model, they're all doing it. So this is what we're going to see. I'm going to look, for example, here at node 1 as a source, but I'm going to analyze it on node 3, and I'll see an entry in node 3's multicast table which says if traffic has come in on interface 11, which is the incoming interface here, for vid 100, now here's the multicast MAC address that I was talking about. So this is the local bit and the multicast bit set, and then the 20 bits of the source. Okay, so that's node 1. And FF, of course, is 255, service 255. So that's the multicast address for traffic coming from node 1 for service 255. And then we see the outgoing interfaces here, 16 and 10. This other one is actually for what the emulated node 12 here will do. With the same address on interface 1, it's replicating to interfaces 5 and 6. So I'll just show that. Okay, so if we look here, I'll just quickly bring this back. Okay, this is incoming interface 11 for this 1FF multicast address, outgoing interfaces 16 and 10, and that's the first one of these entries here, incoming interface 11. Here's the address, and here are the outgoing interfaces, 10 and 11. And these other ones are the other different directions, the other different sources. So this is source 1, source 2, source 13, etc. So because node 1 plays a role in replication for these other sources, it has an entry for each one of them in this particular context, because I've asked for it to do replication. And if you look at the big picture here, and that's what I just showed was all of the state here on node 3. This is the active topology that I was describing, the full set of shortest paths simultaneously. And here we're seeing node 3's contribution in this full active topology, and node 13's contribution for each of the sources that it is a replication point for. Again, we're asking for transit replication, we get the state. If we don't ask for transit replication, it's a head-end replication model. Okay, so I'm going to hand it over to Srikanth, who's going to show you his lab network, and I believe he's going to show some path traces, some of the OANM, and he also has a pre-recorded video showing a network. It's not a network management system. It's a monitoring system, right? Yeah. So I'll turn it over to Srikanth, and then that probably takes 10-15 minutes, and then open it up to questions. Okay.
So we're going to show a demo of one of our lab networks that we, sorry, is it better? Okay, so we're going to show a demo of one of our lab networks which we use for our customers. This demo has a 6-switch SPBM network, 3 PCs connected, receivers for both video and probably even unicast traffic. There's a couple of video servers at the bottom and a few access layer 2 switches in there, right? So the intent of this demo is to demonstrate how easy it is to operate this network by just the VLAN membership propagates by itself in the SPBM network. We'll be showing the shortest path trees, and if this was in one of our labs, you would actually see a live video here. So I'll just start the video here, and most of it is self-explanatory, but I might interject and make a comment or two there. So what you see is, to start with, you have an IC300 on 3 of the devices, the ERS6 at the bottom, ERS1 and 2, ERS1 and 5 at the top. And you got the video server at the bottom with the 2 receivers on the top. So this is an example of a provisioning tool that somebody could be using to provision this network. All you have to do is make the device a member of IC300 and start receiving traffic on that. So this one shows the shortest paths from each of the devices for those trees. What you also see on the links is the monitoring of the actual packet traffic on there, where we monitor the statistics on the link and actually show you that that's the path the traffic's actually taking. So now we have VLAN 3 that's being added on the access side. And now we're going to add an extra switch to VLAN 3 here, or IC300, and this is bringing in the extra IC there. So now ERS2 at the bottom is also a receiver on this video source that's coming from ERS6. What you'll now see is the video source has moved from the server 1 to server 2 at the left-hand side. This is just a simple MAC movement, since it's just all it's really doing is layer 2 MAC move. The VLAN is moving from one source to another from the particular host. And now you'll see there the highlighted path indicates the source is now at video server 2 at the left-hand side corner. We'll show a few simulated link failures on this one, and this one shows the actual path currently being taken for the source. So we're going to do a core link failure there. So you just missed a couple of pings and that's it, and you have your traffic running, and you see the new shortest paths for this traffic that's coming from ERS2 at the lower left-hand side. So we're going to take down one of the switches in the core, and we'll see the traffic again redirect itself here. All of this without having to hand provision any of the VLAN or the ISETs. I mean, all you do is all of your provisioning is pushed off to the edge. The only thing that's ever provisioned in the core is the infrastructure at the beginning when you activate the network, and that's it. You never have to provision services in the core. Okay, so this is a brief demo of how this is supposed to be working. So if you look at this network, and I'm trying to see what is it that the operator has to do to bring this network up. On all of the core-facing interfaces, you enable ISIS, and that's basically it as far as bringing the network infrastructure up. At that point, ISIS has discovered the shortest paths in the network, and you should be able to validate your core network connectivity. And after that, any amount of provisioning only happens where you attach the service access points into this network. You wouldn't need to schedule maintenance windows in your networks to go into the core, and probably even if that particular core devices or core network is operated by another group, you wouldn't need to kind of provision anything else. All the provisioning is pushed out to the edges here. So this was the video demo we had, and I also have access to my lab switches. I'll bring that up shortly. Here's a live lab network that we have running, and we're going to log into some of the switches here. What you see here, all the pink little rectangles that you see at the edges of the network, those are test ports, those are access points into the network, and that's where your services are present. All of the bigger boxes, squares, you see 7 of them, ESP, ESS, CS0, CS1, and the 2 yellow switches at the right-hand side and the green one. Those are SPBM-enabled switches, both SPBM edge devices and the core devices. In IEEE 802.1ah terminology, these would be the BEBs and the BCBs here. So what we're going to see here is see how well 802.1ag, the OAMP, is integrated into this, and also look at our MAC tables to show you that the MAC tables are only present on the edge here. Only the MAC tables are only present on the edges where the services are configured, and then we'll actually log into one of the core switches and see those MAC entries don't exist in the core, because all the core really needs to know is the tunnels. Right, so I'll log into the switch here. There's a CLI session, a couple of CLI sessions we got. So this CLI session here is on the green switch that you see. That's one of the layer 2 switches here. It's got an ISID provisioned. It's got an ISID that says ISID 5010, and it's got it shows this show command here, show ISIS SPBM multicast fib. The VLAN 10 or the BVLAN 10 here is effectively saying that's the algorithm that you're running, and this is your ISID service identified in the core. And this one shows all the switches in the network that have advertised this ISID. This shows the multicast tree for that, basically all the source groups here, right? You see the lower 24 bits of this MAC address here is the group MAC address, a group ID, which is the ISID, and the higher 20 bits, along with the OUI, multicast and the local bit, constitute the source identifier. So what you're seeing here really is the source group entries for ISID 5010, and what you see here is a set of outgoing ports for each of these source group entries, right? So the other things we could look at here, we could show that the MAC addresses are learned remotely. So for VLAN 501, which is mapped into ISID 5010 on this network, I want to look at all the MAC addresses that I have learned from the remote BEBs, right? So here's this. It's got 9 MAC addresses here. It's got 9 MAC addresses here. Here it shows the actual MAC address from the customer side or the access network. Here it shows the MAC and MAC tunnel destination that it's going to. Here it's showing which algorithm it's using. Effectively, the BVLAN 20 is the algorithm it's using. And what you also have here is the ISIS system name of the switch that's advertising from which this MAC address is sourced. So you have an easy way to correlate. If you look at a MAC table anywhere, you can easily correlate where this MAC address is coming from. And it's showing the outgoing port to reach that MAC address in terms of the actual physical port, right? So this is a MAC table, and I'll show you the MAC table on a core switch here for, say, VLAN 501, right? Well, the core switch says I don't have VLAN 501 because it's just transiting. There's no MAC table for that. Just kind of to prove the point that MAC addresses are only on the edge and the core can scale. All you have in the core is really these MAC tables in the service provider network or the BVLANs, right? So this one shows that I got 7 switches in the network, and my entire core forwarding state is 7 MAC addresses. Doesn't matter how many user MAC addresses I have in the edge. That's what I got there, right? Here's, we're going to run a few OAM commands. All these OAM commands are based on standard 802.1 AG. Right? There's no new protocol being invented here. There is no black magic. There's nothing. This is stuff that's been invented for Ethernet all along. And we're just going to run this, right? This is an L2 ping command. The command is being issued on the trunks. Basically, we are troubleshooting the trunks here to see, do I have reachability on my trunks? I'm saying on algorithm number 1, which is BVLAN 10, I want to reach the switch ESP, right? Run your layer 2 command. This says 1 packet transmitted, 1 packet received, 0 loss. This is standard LBM command in 802.1ac, right? Let me run the L2 trace route, right? I'm saying, okay, show me the path on algorithm number one to the same switch, right? It runs the path, waits for all the responses to come back, and what you'll see is the hop count. So what you see, EL2 is saying, I am 1 hop away from EVS. The path is EL2 to ESP. If you go back to this diagram here, right? It's saying on algorithm number 1, I'm going EL2 to EVS to CS1 to ES, to CS0 to ESP. That's what it's saying, right? And you would actually see that's what the output says, right? It's EL2, EVS, CS0, and ESP. And I could run the same command. The second algorithm that SPBM supports in this network. So this network is operating with two of the tiebreaker algorithms that have been defined for SPBM, 2 of the 16. And this shows you a slightly different path where the fork is happening in the network. So if you see this, right, so let me see this. It says EL2, EVP, CS0, ESP, right? So what this is saying is my second algorithm, instead of going this way, is going EVP, CS0, and ESP here, right? And we have one more command. This one actually traces the multicast trees in the network, right? So, okay, you can trace unicast paths in the network, well and good, but you're telling me that your multicast trees are source specific and group specific. Let me see that, right? So this one says, show me my multicast tree for algorithm number 1 for ICIT 510, right? It says, take me all the way to the edge of the network on all the nodes in the network where this tree is traversing, and here's an output here. Right, so here's what you got. You got EL2 is a fork point in this. So let me show you the graphical view, right? EL2, so if you look at the switches participating in ICIT 5010, it's these two here, EL2 here, ESP and ESS, right? So the fork point is here, EVP and EVS, right? Okay. EVP and EVS, and then here's one traffic flow, EVP, EVS, it goes here, and this is another one, EVS forwards to CS1, and this is ESS, right? Same thing. If you see EL2 says, I got one, so if you see this, what this source is the hop count from EL2, from the originating node, from the source. You're saying, I got a fork point at EL2, which is going to EVP and EVS, and it says, I got another fork point at EVS, which is going to the 2 core switches, CS0, CS1, right? And CS0, CS1 don't have any more forks. CS0 goes to ESP here. CS1 is going to ESS, right? And I say, okay, show me the tree for the other algorithm, but for the same group. What you notice here is that the fork point after the first hop is now switched to EVP, right, versus EVS, right? So here's what's happening here is for the first piece of the first algorithm, EVS was the fork point here. 2 paths, this is the tree, and you can go here. For the second one, 2 paths again, this becomes the fork point, and this is it, right? All of this standard 802.1 AG, no new inventions here. If somebody is invested or have their operational folks trained with AG commands, AG mechanisms, AG MIPS, they could continue to use this in this network. The key message here is SPBM is a control plane enhancement to Ethernet. It is not a rip-out of Ethernet and replace everything that Ethernet does with new technology. Right, so I'm all set here. We'll open it up for Q&A.
Yeah, go ahead. Yeah, please do. I think you might have to, is it turned on?
1, 2, 3. Wallace from Georgia Tech. So just a short question. So you mentioned a couple of times you might want to use head-end replication. So when would you want to do that?
So if you don't have a lot of true multicast traffic, if it's just being used for ARP and ARP responses, head-end replication may be sufficient, right? The transit replication is a bandwidth. It's bandwidth efficient. If you do not have a lot of multicast traffic, true multicast traffic, then a head-end replication may make more sense. So you may have a service where one or two of the members are heavy transmitters, and the others are just receivers, or their only participation is for the purposes of ARP, in which case they wouldn't require transit replication. But it's a very easy model to build and allows you to trade the state versus the bandwidth. There's also no computation involved. Right? It's just one shortest path, and that's it.
So is there an issue with multicast, and why would not one just enable it? Is that just because you think there might be like resistance from operators to just switch it on?
Well, it's always important to provide the different trade-offs, right? Mm-hmm. Any one of these protocols has advantages and disadvantages. If you enable a feature that says, I want multicast state everywhere, you will get multicast state everywhere, and if it's not buying you something in terms of bandwidth savings, then turn it off. Yeah, go ahead.
I can add to that. I mean, it is possible that enough times the service that's provided is primarily an E-line service, just a point-to-point service between two switches. What we recognize is you really don't need to install a multicast state for those kinds of services.
Yeah, that's sort of
right.
That's sort of one obvious example, right, is E-line. But from my perspective, state in a network provides you with some payback, right? Every single one of those entries should be doing something to generate a little bit of revenue for you. And if it's not pulling its weight, take it out. But, I mean, feedback on the usability of these things is important from folks that are operating networks. I design protocols and stopped operating networks quite a while ago, so feedback is welcome.
Mike Joseph, Google. Have you given any thought to avoiding traffic disruption during maintenance events and failures? So, for instance, I noticed in one of your tests you dropped some traffic, and it occurs to me that with ISIS topologies, overload is often used for that purpose, but you're doing RPF, so if you don't have perfect convergence, even a head-end node switching paths could cause some frames to flow down nodes which may have already converged and could drop the packets. So have you worked on any topologies where you could actually take a node out of service hitless?
So one of the things that I've breezed over very quickly in the interest of time is a fast advertisement mechanism for ISIS. Because the 802.1 EQ protocol produces very, very efficient multicast trees from itself to anywhere else in the network, and because ISIS can use multicast to advertise its link state, if you tie the two together, which the protocol describes how you can do that, and we actually built a prototype of that a little while ago, you can eliminate all of the ISIS receipt of an LSP up to the control processor and then on to the next hops portion of the protocol. In other words, it's as if all of the ISIS devices were on one LAN for the purposes of distribution of their link state packets. What that essentially translates to is that you can deliver a link state update, which could be a failure or a link metric change at hardware speeds to a network of hundreds and hundreds of nodes, which means the only thing you have to deal with is then the computation and forwarding table production. So we've actually been able to see 20, 30 millisecond outages in that was a 15 or 16 node circular arrangement of nodes, which is the worst possible configuration for a link state because it has to forward the packet all the way around the ring. But there's a lot of thought has gone into how to improve the ISIS convergence rates, and it certainly appears like use of the multicast mechanisms that AQ produces for its customers can also be used for itself. Hope that helps.
My name is Yuri from Comcast. I have a question. So it seems like it seems like that the switches have to connect together, then they have to talk ISIS. If I have a network which has the legacy switches, and how are we going to deploy this? It sounds like to me then I have to upgrade all the switches to do this, or it's not true?
Do you want to talk? Go ahead.
So if your switches are, I mean, one thing you would need is you would need a software upgrade on your switches to be able to run ISIS. But what you would not need to do is rip out your configurations, because if you look at this network here, all it really needs is, if you're running 2 algorithms or 2 ECT algorithms, all it really needs is 2 VLANs in the core. Your existing traffic, if it's running on some of the VLANs, can continue to run as it's currently provisioned, right? So you don't need to forklift your configurations. All you really need to do is upgrade your switches to the new software and then turn on ISIS, and ISIS is up and running. And then you can decide on your own how you migrate your live traffic over to this network. Whether you only add new services to SPBM, or do you migrate your existing services, and the maintenance windows are the time frames over which you actually do the upgrades. We put a fair amount of thought into actual migration procedures. If somebody actually wants to migrate a service, we put a fair amount of thought into actual migration procedures for doing that. And if you see some of these networks here, right, you do see on the access side in particular, you do see dual homed access switches here. These pink boxes, TP2, TP3 here, they're really dual homed. So you do have an option of upgrading one switch at a time while letting the other switch take the load of the traffic for the duration of the upgrade, right? So you will need a software upgrade, and there are dual homing mechanisms on the access that make these migrations simpler. You do not need to forklift any of your configs.
Just talking about the dual homing, one of the things that people are looking at on the standard side is to catch up with some of the proprietary stuff, which has active dual homing. And so this 802.1EQ protocol supports the movement of a BMAC address. So one of the box MAC addresses, we can have multiple box MAC addresses. And so by moving a BMAC address, when one of those access nodes fails, we can avoid relearning as well. So not only does it aid with migration, but it aids with active access and a fast failover without having to relearn all of the associations between the access MAC and the core MAC addresses.
Another question I have is, since some of the MAC address name may be aggregatable, so do you guys think of doing any aggregations, like try to do the aggregation so that you can save some of the link state?
You mean aggregated MAC addresses?
Yep. Yeah, just like what we do for the ISIs, if let's say you want to do a summarize.
Yeah, I mean, that's a really thorny issue because a lot of people will get upset that, okay, it's like IP, it's IPv, you just use IPv6 if you want aggregated addresses, don't do it with MAC, don't do it with Ethernet. I've seen many presentations that show, hierarchical MAC addressing in proprietary implementations, and there's been a few people that have talked about it in standards bodies, but they usually get hit over the head with soft objects.
If you see a network like this, what you see, implementations are possible where the number of MAC addresses in a network, for example, that's completely dual homed or the core forwarding state. I mean, I guess you're trying to say the forwarding state in the core, right, is equal to 2 or 3 times the number of switches. So I got a 100-node network. the maximum number of forwarding entries I have in the core of my network is 200 MAC addresses. That's peanuts for practically any switch that ships today, right? The key point is 99.9% of your MAC addresses are in the user space, and only about a couple of hundred are in the core. So I mean, any self-respecting ASIC today would probably just kind of handle that with no problem.
I guess the idea of separating two flat address spaces, one over top of the other, versus hierarchicalizing one, is something that people have debated for a long time. But this is one address space, one flat address space over top of another flat address space, with learning and association known at the edges. It's the same sort of thing that's done in VPLS and what was the precursor, OEL2 or whatever it was called. Yeah.
OEL2 is a precursor, pre-standard version of MAC and MAC. So, I mean, the view here is that we solve the MAC address scaling problem or the forwarding state scaling problem by just introducing an encapsulation. And given that implementations could limit their core MAC addresses to just one or two, that should be basically that solves any kind of scaling issues that we could see, even up to 1,000 node networks.
I just add one more point, which is it's sometimes easy to get carried away with a good idea and say, hey, this is great, we can do all kinds of massive things with it, and that's certainly not what I think the authors of this protocol are promoting. It's just a better way of doing layer 2 to larger scales. And certainly the hundreds and maybe as many as 1,000. But beyond that, we've got IP. We don't need to be playing around replacing IP with something else. Anybody else? We're pretty much 7 minutes. Okay. I will also point out, if folks would like to learn more about it, there's a Wikipedia. If you go to Wikipedia and search on IEEE 802.1AQ, we've been trying to keep the Wikipedia page up to date. There's lots of references, and there'll probably at some point be a pointer. Maybe you could make this video available off there as well.
Right. So
Yeah. Yeah. Great. Yeah, post it on YouTube. We'll put a link. And also this month's IEEE Communications magazine, I believe the October issue, has an article on shortest path bridging. And of course there's the ITF documentation. And if anybody wants to see the IEEE documentation, just send me an email. I'll give you the password and you can download the big tome. Okay. All right. Well, if there are no other questions. Anybody wants to talk afterwards, we have some emulators here, and you're welcome to play with them. Okay, thanks.